Hello everyone. So in this video we'll be talking more about how to determine the number of bars inside a column for reinforcement and how to determine the diameter. Okay, so what you need to know here first is that whenever you're on site, on a construction site, this is what you see from the column. Okay, so we can see the bottom concrete columns and some steel rebars above, and which are constructed based on this column schedule provided. Okay, so how to arrive at this column schedule, how to determine the number of bars, the arrangement of bars in a column, and the required bar diameter. So, first of all, theoretically speaking, just to understand the design capacity of a column. So, as we know, the column is a compression member which carries axial forces and sometimes bending moments, most of the times actually, because we never have a perfectly axially loaded column. So this is the theoretical capacity P0 according to ACI. AG is the gross area of concrete and AST is the area of steel. So it's the capacity of concrete plus the capacity of steel. Fy is the yielding stress of steel. Okay, so as for the nominal capacity, it's alpha P0. Alpha is a parameter determined by the code and which depends on the shape of the ties. And then from Pn, we can reach the design capacity of the column PD, which is phi Pn. Phi is also the reduction factor determined by the code. So we arrive finally at this design capacity equation. Now, this equation, we use it when we do not, for example, have the dimensions of the column. When we only have like the axial load and we need to determine the dimensions of the column and then the reinforcement. Okay, so for tight columns, we have phi 0.65 and alpha 0.8. And for spiral columns, we have phi 0.75 and alpha at 0.85 because spiral columns contain the column more than tied ones. So for tied ones, it's more subject to buckling and cracks. Okay, so now how to arrive at this configuration. So first, let's discuss some requirements by the ACI code. So for longitudinal bars first, the code requirements are that the raw steel, which is equal to area of steel over gross area of concrete, should not be less than 0.01 and should not be greater than 0.08. So as if the code is telling us that the percentage of reinforcement in the column should be between 1% to 8% of the concrete cross-sectional area. However, it's true that the code allows to reach a percentage of 8%. However, due to in order to avoid congestion at lab places in practice, a maximum of 4% of reinforcement is used. So practically, rho varies between 1% and 4%, not 8%. Okay, this is as for the amount of reinforcement. As for the number of bars, we will be talking more about a practical example, but the ACI code requires that for rectangular columns, at least 4 longitudinal bars are present within the ties. And when we have spirals, like this one, at least 6 longitudinal bars should be present. And for other shapes, at least 1 bar should be provided at each corner in order to avoid any corner cracks. This is for the number of bars. As for the bars spacing, we have maximum spacing between bars should be 150 millimeters. So the spacing between these 2 bars should not exceed 150 millimeters, and between these 2 bars. And the minimum spacing is 1.5 diameter of the bar or 40 millimeter, the maximum of these two. So example, if we have bar diameter, which is 20 millimeters, so this would be 30 millimeters. So the maximum of 30 and 40 is 40 millimeters. So this would be the minimum spacing allowed between these two bars, or these two bars vertically or horizontally, and the maximum spacing is 150 millimeters. Okay, so now if we do not have the dimensions of the column, a practical minimum is 200 to 250 millimeters. Okay, so this width should not be less than 200 millimeters, or this part should not be less than 200. So practically a column, the minimum column size should be 200 by 200 or 200 by 250 or 250 by 250 millimeters. Okay, and this part is so important where the minimum concrete cover to be considered is 40 millimeters. Cover to clear cover. So cover to stirrups to the side of the concrete should be minimum 40 millimeters. This is concerning the longitudinal bars. Concerning the transversal bars, we have two types of bars. We have the rectangular ties and the spirals. Okay, as we have seen in this image, rectangular ties are not connected. It's one tie by itself. However, the spirals are connected along the whole length or height of the column. So, minimum diameter for ties is 8 millimeters to 10 millimeters for longitudinal bars less than 32 millimeters, and 14 millimeters for bars greater than that. As for spirals, the minimum spiral diameter is 10 millimeters. As for the spacing between ties, a maximum allowed spacing is 16 times longitudinal bar diameter, or 48 times the tie diameter, or the smaller column dimension. So depends on this dimension of the column and the diameter of the tie and the diameter of the bar, the maximum spacing for rectangular ties is determined. As for the spirals, the minimum spacing is 25 millimeters and the spacing should not exceed 75 millimeters. And here we can see some typical arrangement of ties. So if we have this tie, these four bars, the tie should be around them. If we have one bar in the middle, we can either use a tie like this, or we can put one more hook in the middle, depends on the shear requirements of the column. And also if we have this type of column, one bar in the middle, we can either put hooks or we can avoid the hooks, or we can put like inclined tie like this. Depends on the design office, depends on the shear requirement, depends on a lot of factors, also on the location of the building and the exposure of the column and whatsoever. So these are just some typical arrangement of the reinforcement. Okay, so let's say we performed a structural analysis of the building and we have our model and we have the required reinforcement percentage from the structural analysis software, like ETABS, for example. So what we do first is we find the percentage of reinforcement required for the column inside the software. Then we draw the arrangement of the rebars required, and then we find the area of reinforcement, total area of reinforcement based on the percentage, which is rho. And then depending on the number of bars, we get the required area of one bar and then the bar diameter. So we will be doing a practical example. Okay, so as for ETABS, let's say we have this building. In order to perform the design of columns in ETABS, in order to be able to find the reinforcement ratios, what we have to do is that we either go to design, concrete frame design, start design check, but first we need to make sure that the design combinations are included, or we can from here do start design check. So what ETABS is doing now is that it's designing the all the frames present in the model, whether the columns or the beams. So in order to view the columns only, what I usually do is that I view only columns and slabs and walls, of course, in order to know the exact location of the column. So I can display design info and then display total rebar percentage in order to get the required reinforcement percentage of columns. So now as we can see, the required reinforcement mostly is 1%. Okay, so most of the columns need only 1% reinforcement, which is translated to that the total area of steel required in the column is 0.01 times the cross-sectional area of the concrete column. Okay, so we can take one column as an example. Okay, so let's consider this column, which is 400 by 600. And this column is directly to the right of the core. Okay, so if we go in plan, okay, so we select this column. We make sure that the column is selected in all the floors. This is the joint. Okay, and we show selected objects only. Then we check the column in 3D. As we can see, there's one of the columns which is not selected. So what we do is that we select this again, and then we show all objects, and then we go back to check where was the column not selected. This is it. Okay, show selected objects only in 3D. So as we can see, the required reinforcement percentage for the column is 1% from bottom to top. Okay, so this column was 40 by 90, and then 40 by 70, and then 40 by 60 for the rest of the floors. Okay, so if we begin by the 40 by 60 column, okay, so what we do first, okay, so we draw the column, which is 600 by 400. Okay, so this is my column, the concrete boundary. Okay, let's change the annotation type. Okay. So as we mentioned here, that the concrete cover is 40 millimeter, clear cover to stirrups. So we go here and then we offset this column. First, let's join them. We can type join. Okay, so now it's a polyline, or we can draw a rectangle or polyline from the beginning. Okay, so we offset this. It says here specify offset distance, so it's 40 millimeters. Select object to offset, it's this one. So this is the boundary of my stirrup. Okay, so let's choose the correct layer for this, which is the reinforcement rebar. Okay, now that I have my stirrup, I need to insert my bars. The number of bars and the arrangement of bars in a column is different from an engineering office to another engineering office. Depends on the way they work, how they put the bars, whether 3 bars in a 400 or 4 bars or 5 bars. It depends, but the important thing is that the minimum and maximum spacing limits should not be exceeded. So the minimum spacing is maximum spacing is 150 millimeters, and the minimum spacing is the maximum of these two. So one school says that if I have a width of 200 millimeters, I place 2 bars. 300 millimeters, I place 3 bars. Starting from 400 and above, I place 1 bar less. So 400 millimeters is also 3 bars. 500 millimeters is 4 bars. Okay, 600 millimeters is 5 bars, and so on. 700 millimeters is 6 bars, and so on. Okay, so what we do now is that I should place 1 bar at each corner. This is my start. So let's use this bar. Ultimately, the bar should be drawn in the correct diameter, but here it's just for the purpose of checking the bar's arrangement. So I should have 1 bar at each corner. So this is the first thing I do. Okay, in the 400 width side, I need to place 3 bars. But I also need to check that my spacing limits are acceptable. So the bar here is placed in mid-distance between the 2 bars because I should have my bars well arranged and symmetric. Okay, so this is the first one, and the same should be drawn on the other side. Okay, and I need to check that my spacing is okay. So I have clear distance, which is 120. Okay, it's not exceeding 150, so I'm fine, and it's for sure greater than the smaller limit, which is around 40, which is also okay. So I'm fine on this side. Some design offices put 4 bars in a 400 millimeters width, so it depends. Now, as for the 600, I need to place 5 bars. So between the 5 bars, I have 4 spaces. Okay. So what I can do, for example, is that I need to measure the distance here, which is 495, and I need to have 4 spaces in between. So I divide this into 4 spaces. So this is 1, 3 bars, and 4 bars. Okay, so now I have 1, 2, 3, 4, 5 bars here in the 600 face. But again, some design offices place 6 bars in this, some place 7, depends. But the important thing is that the spacing limits are well taken into consideration. Okay, so this is not exceeding the maximum allowable spacing, which is 150 millimeters, and it's not less than the minimum. Okay, so now I should have the same arrangement on the opposite face. So this is my bars arrangement. So in this column, I have 3 bars, 6, 7, 8, 9, 10, 11, 12 rebars. Okay, now as for the stirrups, as we agreed here, there are a lot of different stirrups combinations and arrangements, and it's all a matter of decision of the design office working or the project requirements or the shear requirements based on ETABS. Okay, so the important thing is that only one row of bars can be free of stirrups, which means that my stirrups cannot be, for example, like this, because here I have this is without stirrups, this is without stirrups, and this is without stirrups. Okay, here let's not forget the hook. Now, for drawing purposes, I'm just drawing it like this because this is not the aim of the video, but there should be a well-defined stirrup drawn just like this one, with the curved bars and the hook in a correct manner, because all of this is taken into account later on in the bar bending schedule and length of the stirrup. Okay, so what I can do here, I have several options to do here. The first option is that I can have a hook on these two bars. So let's say this is a hook. Of course, this is not how a hook should be drawn. So if I place a hook here, I have one row of bars with a tie, another row without, another row with, another row without, another row with. So this is completely fine. Okay, another option for the stirrups is that I can place a smaller tie here surrounding these two. So in this way, I would have only one row of stirrups without confinement, only one row of bars without confinement, which is completely fine. The difference between the two options is that in this option, I have four legs of ties or four legs of stirrups. In the other option, which is the hook, I have three legs. If we remember this one, I have one, two, and three legs. So depending on the shear demand of the column, we can place the stirrups. If this is fine for the shear demand, we can leave it just like this. If we need an additional stirrup, we can go with the next option, which is the stirrup over here. And also, I cannot do this on a side note, because the reinforcement in a column needs to be symmetrical with respect to its center. Okay, so if we consider this column, the center is here. So here we have a tie, but here we don't have a tie. So the confinement should be symmetrical. So it's better to do it this way. Okay, and now as for this side, we don't need an additional stirrup here. We can place a hook if needed, but if we don't need it for the shear demand, we can keep it just like this. So this is for the 400 by 600 column. If we have, for example, we need to also mention how to calculate the diameter of the bar. In order to determine the diameter of the bar, of course, in order to do the column schedule, we need to inform the construction workers on site and construction engineers that the diameter of bars we have and the diameter and spacing of the stirrups in order to construct the column accordingly. Okay, so and for this one, the stirrups. Okay, here we need to annotate the two stirrups that we have. Let's just get these from here. So just to know what the annotation is, this is the number of bars, and this is the bar diameter. This symbol is for bar diameter. This is the number of stirrups, the diameter of stirrups, and the spacing of the stirrups. So 4, 2, 8 at 200, for example. Okay, so here we have a total of 12 bars. Okay, so in order to determine the diameter, as we said here, we have reinforcement ratio of 1%. So going back to this slide, we have the reinforcement ratio and we have the bars arrangement. We need to get the steel area, the bar area, and the bar diameter. So here, we have reinforcement ratio of 1%. Okay, HE is the area of concrete, which is 400 by 600, which is 240,000 millimeters squared. Okay, so the area of steel is equal to rho times area of concrete. Rho is 1% over 100 times the area of concrete. So we have total steel area required is 2,400 millimeters squared. Okay, so now we have the total required reinforcement for all the bars. So in order to get the area for one bar, we need to divide the area of steel by number of bars, which is 12. So we have an area of the bar is 200 millimeters squared. And then from the area of one bar, we get the diameter. So diameter is equal to radical 4 times area of one bar over 4. So which is equal to 15.95 millimeters. Of course, we don't have this bar. So the bar chosen is Tor 16. Okay, so if we now go back to this slide, the percentage is 1%. The required steel area is rho AG, where AG is this one, and then rho AG is this one. So we have 2,400 millimeters squared total. The required area of one bar is we divide the total area by the number of bars, and then the diameter is this one, which is 15.95. Just a side note, this comes from that the area of one bar is equal to pi squared over 4 because the bar is circular. So this is the area of a circle. So now, having that, we need Tor 16 here. So this is Tor 16. So if we want to calculate the total area of steel, if we provide a bar of Tor 16, we have total steel area is equal to number of bars times area of one bar, which is pi times 16 squared over 4, which is equal to 2412 millimeters squared. Our requirement was 2400, so this is okay. Now as for the stirrups, here we have 2 stirrups, okay? We don't count the legs, we count the number of stirrups. So it's 2, not 4. Again, depends on the design office. Not all offices follow this pattern. Okay, so as for determining the diameter and spacing, for each diameter and spacing, we have a certain shear area that is covered. Okay, so we calculated by the equation which says area of bar of the tie bar, of course, let's call this tie, times number of legs divided by spacing times 1000 in order to take it per meter. Okay, so we get the result per millimeter squared per meter. Okay, this is how we calculate how much each one covers. So a bar of Tor 8 at 200 covers until 502.65 millimeters squared per meter. For tour 8 at 200, we cover 670.2 millimeters squared per meter, and so on. We use bars 8, 10, 12, 14, 16. Some countries use bar 18, some countries don't. 20 and 25, then 32. So let's for now consider this. So in order to determine the required stirrups, okay, display design info, shear reinforcing. Okay, so here we have the required reinforcement area for shear. We make sure that the units used are millimeter squared and meter for this unit, or else we cannot use these limits. So if we're considering this column, which is 400 by 600, the requirement is 500 millimeters squared per meter, which is covered by this limit here. So we can use this limit, and don't forget that this limit is only for 2 legs. So if we are using 4 legs of stirrups, then we have double this limit, double this number, so it's almost 1,000 millimeters squared per meter. So we can use tour 8 at 200. Okay, because here these numbers were for only 2 legs, so for one stirrup only. This is 1 leg and this is 1 leg. However, here, since we have 4 legs, so the number provided is 1,000 millimeters squared per meter. Okay, now let's consider another column, not the same column, but at a different level. So because here we have 1%, here we have 1.65%, 1.75, and then 1%. Okay, we already did the part above, which is the 40 by 60, considering the 1%. So now if we want to do this column, which is 40 by 70, considering 1.65%, okay, we can make use of this one. But of course, it's better to redraw it from the beginning. Okay, so we can remove these because we need to redraw them. We can keep 2 bars here only, but here now we should have 6 bars, so we have 5 spaces. So we first measure the distance between these. So we now have 1, 2, 3, 4, 5, and 6 bars. Of course, we make sure of the clear spacing between them, which is not exceeding 150 and not less than the minimum. And then we can mirror them to the other side. Okay, in order to mirror, we write MI, and then we can mirror them this way. So here, erase source object, no. This is the bars. Now for the stirrups, as we said, we cannot leave all of these without stirrups. So the perfect thing to do here, okay, if we consider what we did previously, we cannot do the same here because if we did this here, and considering the symmetry, we have 2 rows of stirrups that are not within a tie. So the better thing to do is to keep the symmetry. We can do this stirrup. Okay, so here we have Tide, no tide, 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 no tide. Okay, so we don't have more than one row of stirrup untied. Okay, so now in order to move, we write and then it's move. Okay, so now instead of 12 bars, we have two additional bars because we have one additional bar here and one additional bar here. Okay, so now we have 14 bars. So this is 6, 12, 13, 14. So here we have 14 bars. Again, in order to find the required diameter of bars, we perform the same procedure again. So we have reinforcement ratio 1.75%. Gross area of concrete is 280,000. Steel area is equal to 1.75. Then area of one bar is equal to, and then the bar diameter is equal to 21. Now, in some countries, we have a bar of diameter 22. In some countries, we have directly 25. So we need to take the bar directly above this quantity, which is toward 25. Depends on the region you're in, depends on what you're working with. Door 25 is bar diameter of size 25 millimeter, diameter 25 millimeters. And now for the stirrups, we show display design info. So it's 583.33. Okay, as we said, Tour 8 at 204, 4 lakhs cover until 1,000. So we're fine with this value. Okay, so now if we just take an example of other dimensions, other column dimensions, if we start with the width of 200, as we see here, we have two bars in the width of 200. We have three bars in the width of 300. And here, as we said, we can use the stirrup or not, depending on the design office, but it's better to keep these confined in such a small squared column. For 400, here we used 4 bars, sometimes we use 3 bars, it depends. Okay, for 50, we also use 4 bars, 4 bars for a column of 500. For 350, here we use 3 bars. For 600, we used 5 bars. For 800, as we can see here, it's 1, 2, 3, 4, 5, 6, and 7. For 900, it's 8. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, for 400, it's 4. For 1,000, it's 9 bars, and so on. Okay, now this is a circular column. The most important thing is that we have at least 6 bars, and we arrange them symmetrically such that we don't exceed neither the minimum spacing nor the maximum spacing. And if we have irregular columns, we consider as if this is one column here, as if this is one column here, and we arrange them accordingly, and this is one column here. Okay, so we distribute the bars in this way and this way, and these two bars would be common between the two. We then distribute them here and here. So now just to see some stirrups arrangement. As we mentioned, we need to keep them symmetrical and without two bars in a row unconfined. So here we have this type. Let's see if we can do another arrangement. For example, if we can try this one. Okay, so since we need to keep them symmetrical, we avoid this one and we put it at this one. Okay, maybe we can provide a hook here. But the stirrup is sometimes preferred than the hook. So this is another arrangement of the bars, of the stirrups. And of course, here we need to mention that we now have 2 stirrups instead of 3 plus 1 hook. So here, in order to keep it symmetric, and because if we don't have this, we will have 2 bars unconfined, so we don't have any other options. Same one here, same one here. Okay, we consider this one. Here, since we have 4 bars, we need to also provide confinement in the other direction here. And of course, we have 1 stirrup, 2 stirrups, and 3 stirrups because we have an external one. So here we have 3, 2, or 8. So as if we have 4 legs in this direction and 2 legs additional in this direction. Same one here. And it's all in the same concept. So now, if we consider this example, now let's say we don't have a column size and we don't have finite element model. We can get a PU from the tributary area method that we talked about in a previous video. Okay, and we choose a certain f prime c and fy, and we can assume first rho g is 0.01 or 0.02, but the minimum is 0.01. So the first thing to do, since we don't have a column dimension, is to find the column dimension. So here, okay, so here we need to notice here we need to put attention that this is a squared tight column. Okay, so the first step is to find the column dimensions. In order to do so, we need to use the design capacity equations shown here. Okay, so this is the design capacity. Okay, we have phi is 0.65 for a tight column, and then alpha is 0.8. AG is unknown. It's our unknown in this equation, and AST is 0.02 AG. Okay, so we have here the capacity is taken equal to PU just as a beginning of a design. So this PU is used here. Okay, so we now have an equation with one unknown, which is AG. So AG, which is the reinforcement, the gross area of concrete, is shown here. So then we have now AG. So since we have a square, so this is the area of a square, we can find the area. We need smaller than it, so we try A for 100 millimeter, which provides this cross area. Okay, so now using the same equation, we now have to find the required steel reinforcement. So this is the required steel reinforcement for a square of 400 by 400. We can provide either 3 bars by 3 bars or 4 bars by 4 bars. Okay. So providing 3 bars on each face, we have a total of 6 bars, which lead to an area of 36.94 centimeters, which is greater than the required area, so we are fine. And this is between 1 and 8, so it's acceptable. This is the detailing of the column, and then the checks for the spacing between the bars and the choice of the stirrups.